Okay, so there's this classic bumper sticker that says, if you can read this, then you're too close. And what it means is kind of stop tailgating me, right? Stop following so closely. If you can read this, then the letters are big enough. That means that you must be too close in order to be able to read it. Now they're saying here, okay, so this company accidentally printed the message wrong, and if we took this message, then are these also true? And by the way, we learned about the idea of counterexamples, so if we can come up with a counterexample, then we can say that that's false. So if you can read this, you're too close. We're going to assume that that's true, that the only way you would be able to read it is if you were close enough that you were driving too closely. So what about this one? If you are too close, then you can read this. True? Well, maybe you are too close, but you can't read it for some reason, like you don't speak the language or your vision is terrible, right? So there might be reasons why you are too close, but that doesn't mean that you can read it. What about this one? If you cannot read this, then you're not too close. For the same thing, maybe you can't read this because you don't speak the language, but that doesn't mean that you're not too close. It just means that the reason that you can't read it is not because of your distance, but because of your language ability. What about this one? If you are not too close, then you cannot read this. Well, the only way that you could read it is if you were too close. So if you were not too close, that implies that you're not going to be able to read it. So that one's true. The original one's true. A is false. B is false. But C is also true. This is going to be something that you're going to notice as a pattern when we do these, is that this one and this one will be true, and these will be the same, but not necessarily also true. By the way, we'll get to specifically the definition of each of these shortly. Now, the foundation of reasoning, as it says here, are these if-then statements. We call them conditional statements. They're conditional because only if this certain condition's met, if this is true, then we can also determine this, as long as the if-then statement or the conditional statement is a true conditional statement. Okay? But if this, then this, right? This leads to this. So we can use this in mathematics as well. And here's what we've got. We've got a conditional statement is an if-then statement. And we say P implies Q, meaning if we know the first part is true, then that will lead us to knowing that the second part is true as well. Or more specifically, the hypothesis and the conclusion, because the hypothesis is not always at the start, as you may have seen in the warm-up. Okay, so the hypothesis is the if part. If P, then Q. Or if P is true, then Q is true. The conclusion, and they also say P implies Q. Knowing P implies that we also know Q. P is contained within Q, so if you know you're in P, or if you know that this is true or you're here, you're also here. And that conclusion is the then part of this. Okay. Again, this Venn diagram illustrates how the set of things that satisfy the hypothesis lies inside the set of things that satisfy the conclusion. If we know this, then we know this. All right. We're identifying the hypothesis and conclusion, and there's an important bit of this to note. We want to know, for this statement, if an animal is a robin, then the animal is a bird. What is the hypothesis and what is the conclusion? Well, you'll recall that the hypothesis is the if part of the statement, but it does not conclude if. It is what follows if. An animal is a robin. That is the hypothesis. Don't put if and don't put then when identifying hypothesis and conclusion. Okay? So then, what is the conclusion? The animal is a bird. Okay? Those are the two parts, and we will learn how to use those later to do other things, but you need to not have if and then in the statements. Okay? What would the Venn diagram look like for this? Well, specifically, if it's a robin, it is definitely a bird. All robins are birds, and so this group robins is fully contained within this group birds. Here's your got it problem. See how you do. Identify the hypothesis and conclusion. Okay, so let's say we want to take some statement like vertical angles share a vertex and write it as a conditional if-then statement. What do we need to do? Well, we need to identify what part is the hypothesis, and really what you're looking for is there something that if we knew one part of this, we would then know the other part of it? Okay, and here's what it says. For two angles to be vertical, they must share a vertex. So we would know that if they were vertical angles, then they would share a vertex, okay? And we can then say, we know that this is the part that we must need to know in order to know this. It doesn't work the other way. If we knew they shared a vertex, that doesn't automatically make them vertical angles. Okay, so what does that look like as a statement? If two angles are vertical, then they share a vertex. Try this got it problem. All right, now, the truth value of a conditional. It's either true or it's false. So to show that a conditional is true, you need to show that every time the hypothesis is true, we know that the conclusion is also true. And just to give you an example, I can say a conditional statement, if I show up to work every day this year, then I will be given $1 billion. That's certainly a conditional statement, but that is not a true conditional statement. Because if I show up for work every day this year, I'm not going to be guaranteed $1 billion. Got it? So you can say a conditional statement doesn't automatically make it true, and you need to determine whether it is true. Now, here's how you can do that. A counterexample, oh, I love these, can help you determine whether a conditional is with a true hypothesis is true. So to show that a conditional is false, you need to find one counterexample for which the hypothesis is true, but it doesn't mean that we get a false conclusion though. Okay, so then the whole thing would be false. For example, I know that there's a situation where it could be true that I do show up every day to work. Okay, but so that's the hypothesis. The conclusion that I get $1 billion, no, not true. Okay, let's apply this to some real problems. So let's do it. Let's see if the conditional is true or false, specifically if it's false by finding a counterexample. If you can't find a counterexample, then you've got to be careful to claim something is false if you can't show a situation where it's false. So don't say it's false, but I don't know why. Okay, come up with a counterexample. If a woman is Hungarian, then she's European. Yeah, that's true, because Hungary is a European nation, so anybody that's from Hungary is from Europe. So that is a true statement. And you can just logic that out. You don't necessarily say, I can't find a counterexample. It's just like logically, yeah, that's part of the European Union, so they're European. What about this one? If a number is divisible by 3, then it is odd. Actually, every other multiple of 3 is even. 3, then 6, then 9, then 12, then 15, then 18. And as you can see, this statement is false. The number 12, the one condition or the one counterexample we need to find in order to just prove it's false, the number 12 is divisible by 3, but it's not odd. And you only need one, even though there are more that are available. So try these got it problems, see how you do. All right, so here we're talking about the negation of something or not that thing. The negation of a statement is the opposite of statement. For example, oh, and by the way, they use the symbol, this wavy thing, which is different in this case than it might be if you saw it for congruent or whatever, okay? That means not P, not P. So the negation of this sky is blue is the sky is not blue. Simple. You can use negations to write statements related to a conditional, the kinds of which we're going to learn in a second. Every conditional has 3 related conditional statements. Let's see what they are. All right, this slide is chock full of information, so try and absorb it, but it'll all flow for you, and I'll give you some hints. Okay, so your original conditional, right? You use the given hypothesis and conclusion. You say if hypothesis, then conclusion. P implies Q, or if P, then Q, right? The converse, and I want you to remember it like this, the converse exchanges the hypothesis and conclusion. So you say if the original statement's conclusion becomes the hypothesis, if angle A is acute, then, and the original conditional's hypothesis is now the conclusion, or Q implies P, if Q then P. The way that you can remember it is that, think about your Converse sneakers. You can just take your feet and you can swap their position, right? You can just step left foot over right foot so that you're kind of standing with the feet in the wrong sides. And that's kind of how you can think of the converse. They just switch position, okay? So if angle A is acute, then measure of angle A equals 15. We'll talk about whether it's true or not in a minute, but the inverse involves the negation of it. Inverse is not the converse where you just switch the positions like you can switch your feet, but is negating it, both of them. So you say, start with the original conditional, but do the negation of the hypothesis and conclusion. So if measure of angle A is not 15 degrees, then angle A is not acute. Not P implies not Q, or if not P, then not Q. Okay? And the final one is the contrapositive, which is just both. You switch positions and you negate them. You do both of these things. Contrapositive is both of those things done together. So the original conclusion becomes, when negated, becomes the hypothesis of this one. If angle A is not acute, then, and the original hypothesis negated becomes this one's conclusion. Then measure of angle A is not 15. Okay, or not Q implies not P. If not Q, then not P. Sounds like a lot of information, but you'll get flowing at it. And the big thing to remember is you can just switch the position of your feet, and you can, that's what it means to be the converse, like Converse sneakers, and that's going to be the key to remembering it. So let's examine that original conditional statement, its converse, its inverse, and its contrapositive to see their truth values. Okay? The conditional. If the measure of angle A is equal to 15, then angle A is acute. Yeah, all 15-degree angles are acute. That's true. What about the converse where we switch them? If angle A is acute, then the measure of angle A is 15 degrees. No, there's a lot of other measures that are considered acute. Angle A could be acute, but it's not 15, it's 45, for example. So this, knowing it's acute doesn't automatically mean that you know its measure is 15. That's a false conditional. The inverse of the original conditional is, remember, you negate it. If the measure of angle A is not 15 degrees, then angle A is not acute. Well, again, for the same reason, and this is a secret, you can use the same counterexample for the converse as you do for the inverse. Maybe measure of angle A is 45 degrees, just like I set it up here. If the measure of angle A is not 15 degrees, for example, it's 45 degrees, does that mean it's not acute? No, 45-degree angles are acute, so that's false. What about the contrapositive, where you switch them, their positions, hypothesis and conclusion, and you also negate them? If angle A is not acute, then the measure of angle A is not 15 degrees. Yeah, that's true. If it's not acute, then it's not in the range of 0 to 90, so it can't be 15. The conditional and the contrapositive will also have the same truth value. These two will have the same truth value. These will have the same truth value. Now, it could be that they're all true or they're all false. Just know that these two will have the same, whatever they are, and these two will have the same. And in fact, if these are false, they'll have the same counterexample for it. So a conditional and its contrapositive are equivalent statements, therefore they'll have the same truth value. They are either both true or both false, and the converse and the inverse are also equivalent statements. They're either both true or both false. All right, so what are the converse, inverse, and contrapositive of this following conditional right here? If the figure is a square, then the figure is a quadrilateral. We're going to determine the truth value of each, and then we're going to give a counterexample if it's false. So this is the statement. If the figure is a square, then the figure is a quadrilateral. What are we going to do about this? Well, here we go. We identify the hypothesis and conclusion, which is the hypothesis is the figure is a square. The conclusion is the figure is a quadrilateral. And then so that's the first thing that we do. We're now writing the converse of this. So we switch the positions of them and we say if the figure is a quadrilateral, the conclusion now becomes the hypothesis, then the figure is a square. The hypothesis becomes the conclusion. Okay? If Q, then P. Is that true that if a figure is a quadrilateral, then the figure is a square? Not necessarily. It could be a rectangle or something, right? So we say that the converse is false. Okay, let's keep going. We're going to do the inverse now. Remember where we take the negation of each. Okay, to write the inverse, negate both the hypothesis and conclusion of the original. So we say if a figure, a rectangle that is not a square, sorry, is what we're talking about. So if a figure is not a square, then the figure is not a quadrilateral. Well, again, it's going to have the same truth value as the converse and the same counterexample, which is if it's not a square, it could be a rectangle, doesn't mean it's not a quadrilateral. Okay, and they give all of these examples here. These are all four-sided figures, quadrilaterals. Now, the contrapositive is to both negate and switch their position. Okay, if not Q, then not P. And what does that look like? If the figure is not a quadrilateral, then it is not a square. Well, you can't not be quadrilateral, but you can be a square, so that's true, which matches the original statement's truth value, which is true that if a figure is a square, then it's a quadrilateral. Okay? Here's your got a problem. See how you do. All right, I hope that you actually kind of find these neat and fun. They're going to get more fun the more you get comfortable with them. So do try this lesson check and see how you do.